Welcome, class. We're going to pick up in our third week now that we've been meeting online. I want to thank the students who met with me last week on, especially Friday and Wednesday. You've given me some good feedback about things that we could change, perhaps different workflows that we could look at. Some of you have contacted me because your assignment is late and you've noticed that some of the things have closed and you're not able to submit work now. If that's an issue for you, at this point, I'm okay with opening those items back up and letting you complete them. So email me and let me know what your situation is. Best way to get a hold of me for any specific assignment is just leave classrooms comments rather in the classroom on that assignment, and I get notified, and I'll look at that right away. We're going to start today by looking at kind of a review. I want us to review what we've learned about systems of inequality so far. So I've got here this system of inequalities. It's clearly not linear. The first one's exponential. The second one is linear. And I just want us to graph those and identify where the solution for that system is. So the first one is fairly straightforward. If I was going to think about making a table of values for this first one, I could say, well, here's my x values and here's some y values. And it might be nice to look at a couple negative x values. So I might start with -2, -1, 0, 1, 2, 3, and maybe 4. I know that when x is 0, right, this becomes 2 to the 0 power, so that just simply becomes the number, anything to the 0 power is just going to be 1. When x is 1, this would be 2. When x is 2, this would be 4. So if you look at what this is saying take 2 and, in this case, square it, raise it to the third power, this would be 8. Raise it to the fourth power, we'd be at 16. And if I was at -1, this would be 2 to the -1, which would be a half, and 2 to the -2 would be 1/4. So on a graph, I probably should use a different color for this. Let me use this kind of green. So -2, when x rather is -2, we're looking at 1/4. When y is -1, we're looking at a half. When y is 0, we're at 1. When y is 1, we are jumping to the number 2. And when y is 2, we're going all the way up to the number 4. 3 is sending us to 8. And 4 is going off the scale up at 16 there. So this says it's a greater than strictly, so I know that my boundary has to be a curve. So I can fill in the boundary by just making a dashed line through these points. So there we go. All the points on that curve are not included in the solution set, but that's our boundary. And also it says that y's are those things that are greater than that curve. So my guess, if I put in 0, 0, it would not work. Again, I like to test this point 0, 0 because the number is easy. When I'm looking at the equation, y is greater than 2 to the x power. If I put in that x is 0, this is 2 to the 0, and then y is 0. So this is saying 0 is greater than 1, which is false. Because that's false, I know that I'm going to be shading above this curve. So all the points above this curve are solutions. And it makes sense in context of reading this, the way that it's written with the y first. It says y values are those things that are greater than the curve. Y's are greater than the curve. For the next one down, it says we're going to look at this is a linear relationship, right? X plus 4y is less than or equal to 4. And to deal with that, I'm going to go ahead and get this in slope-intercept form. So I'm going to subtract x from both sides. This is going to become 4 times, oh, that's interesting, 4 times y is less than or equal to the opposite of x plus 4. And then I'm just going to divide both sides by positive 4. So this should be y is less than or equal to -1/4 x and then plus 1. So I see my y-intercept and I see the slope pattern, so let's pick a different color for this. We'll go with this kind of uh, blue or periwinkle or something. So at when x is 0, right, this is going to be at 1. So I've got the same exact y-intercept. Now, it's that point that I've just highlighted in blue is not a solution of the original inequality. So it won't be a solution for the system either, but it is a point where I'm starting here. And then my slope pattern is down 1 and over 4 units. So this is a point, down 1 and over 1, 2, 3, 4. This is a point, down 1 over 4. This is a point. And I can also go up 1 and then back 1, 2, 3, 4. So here's another point. So that's my boundary. From those dots, I can see it. And this boundary, now I've made a mistake. I can see that 1, 1, 2, 3, 4. No, 1, 1, 2, 3, 4. Down 1 over 1, 2, 3, 4. Down 1 over 1, 2, 3. That looks good. All right, so I'll line up these, and I'm going to draw this as a solid boundary because this one says y's are their y's are less than or equal to. So the or equal to is why this is a solid boundary, and it says less than or equal to. So for this curve, where if I plugged in 0, 0, I expect it to work. And yes, 0 is less than or equal to 1, right? 0 is less than or equal to 1. That's true, so we're shading in the things below. Now, if I'm really concerned about the parts where both work, so let's pick a different color altogether. We'll go with this kind of orange color. So in here, not including the lower boundary, right? But everything below the blue curve, including the blue curve, and those things above the green curve, it's a blue line, right? Everything below the blue line and above the green curve are solutions. So our solutions, everything in that region. Now, of course, that's great. If we're just limited to paper pencil, it's nice to be able to look at that, make sure that we can modify an equation so that it's easier for us to graph. But it's also fine to use graphing tools. So you could go ahead and pull up Desmos. In fact, let's do that. All right, so that first boundary was y's are those things that are greater than x raised to the not x raised to the 2 raised to the x power. And there we go. We can see the original, the curve that we had. It's pretty similar to our graph that we did on quote unquote paper and pencil. The other one, let's just graph this as is. So this was x plus 4y is less than or equal to the number 4. And that looks pretty similar. I think that is what we got. It's kind of nice to come over and think about, okay, so I did modify that equation. Maybe I should graph my other version. I could just verify that I got that correct. So if I wrote this as y is less than or equal to negative 1/4 x and then plus 1. What I can see here is that, yeah, these two equations are indeed equivalent to each other. They have well, these inequalities. They have all the same points. They have the same boundary, and they're both shaded in the same direction. So again, the points where we're looking at our solutions are those regions that are shaded by both. So it looks to me like the smallest x value that would work would have to be negative 1. And the reason why is I can't plug in 0 as the smallest x value that would work, because although it would work for this line, right, and everything below it, it is not in the solution set for this curved one, because this y's are y's are greater than 2 to the x doesn't include the boundary. So my smallest x value that has a solution would be negative 1, and then the y would go with that. For example, right, there's lots of numbers. If I'm restricting myself to integers only, negative 1, 1 would be the smallest, or the first x value that would work. Actually, it would be the largest x value that would work, wouldn't it? Smaller than that would be negative 2. Negative 2, 1 would be a solution. Negative 3, 1's a solution. Negative 4 and 2 is a solution because it is on this line, right? And that negative 4, 2 is a point that's on this boundary. So I'm just picking integer points. All of the points in between work. So like negative 1.5 and then 1/2 would work, negative 1.5 and 3/4 would work. So anything in here works, but if I'm just looking at integer values um, that are just easier for me to identify, those are all values that satisfy both. All right, so that's just kind of a review of what it looks like to graph a system of inequalities. In this case, they're not both linear. One was linear, one was exponential. And we're finding the xy value, xy points that satisfy both, and they're all in this region. And I guess kind of setting the stage for our next problem, both of these are considered constraints because they're setting constraints on where I find values of xy pairs that solve a particular problem. And I only have 2 constraints here, but you can see with these 2 constraints, instead of just looking in the entire Cartesian coordinate plane, which is vast, right? I'm looking over in this area only, and points over in this area are solutions to this system. Points over here are solutions to neither one of the inequalities. Points here are solutions to just the exponential curve. Points down in here are solutions to just the line, the linear relationship. But points in here are solutions to both. So I want to just reiterate this idea of what's a constraint and what it does. All right, so in fact, no, that vocabulary doesn't appear here. Okay, so let's move on to our next problem. Okay, so I'm going to set this up here, and this will be one of the problems that you'll finish today on the doc that you turn in. And then I'll do a separate assignment for the homework for today. So search and rescue. I'm completely lost. So this problem, what it is just kind of an overview, is this problem is going to describe a series of constraints. And I think there's 4, or maybe there's just 4 constraints. And we need to take those constraints that are not going to be given to us in the multiple representation of a table or an equation or a graph. They're going to be given to us as a situation, and we're going to have to read that situation and come up with the equation representation so that we can use that to come up with the constraint that'll help us decide where to look for things. So the idea is that a hot air balloon is crashing somewhere, and we have a series of constraints, and we're going to constrain where we look for the crashed balloon by using these constraints. So I'm completely lost, water everywhere. I can see both burners have failed. Wait, I see land. I'm going to try and land. I think those were the last words from Harold in his hot air balloon. The last time the balloon showed up on radar, it was near the Solomon Islands in the Pacific Ocean. Your task, your team. You're not with a team today, are you? You're alone. Feel free to reach out to people, and you can form teams. In fact, you can think about the last team you were at, but you can get together and work with people. You can talk to me today during office hours too if you want. But your team must determine where to send the search and rescue teams. Use the following reports along with the map on the lesson 9.3.2 resource page, and look carefully for information that will help you draw constraints on where the balloon might be found. Give the search constraints to the search and rescue team as a system of inequalities. Be sure to identify the probable landing site on the map. So we're going to see 2 things: a series of constraints, right? Those are going to be equations, system of inequalities that you turn in to me. But also you're going to have a graph where it specifies the area that we should be searching. So if I go on to the next page here, these are in your book. You can look at this from there. But here they are. Basic facts of the case. The balloon departed from the airport at the northern tip of the Philippines. The flight was supposed to follow a straight path directly to an airport in French Polynesia. Okay, we need to see the map of what this is looking like. Okay, so this map rather might be helpful. So again, the balloon departed from the airport at the very northern tip of the Philippines. So the map that our textbook gave us looks like this. Oops. And the Philippine Islands are right here. And it says that the balloon departed from an airport at the very northern tip. So right there is where the balloon departed from. The flight was supposed to follow a straight path directly to an airport in French Polynesia. So it was supposed to go along here. So if I think about it, this can be a boundary line. So I can draw this boundary line, but in order for me to describe that, I'm going to need to figure out what this equation is. And I'll tell you that probably the best thing you're going to want to do is look at this in GeoGebra, and we might do that a little bit, and see if you can get click and create a line from this point to this point. The other thing that it says the balloon's last known location was negative 1,000, 1,000. So I want to point out that the scale factor for this particular map is that this distance, these units, are each 1,000 kilometers. So if I'm at negative 1,000, positive 1,000, right, that means that the balloon was down here. Now, relative to this boundary line from here to here, it looks to me like I'm below it. So I think one of my constraints is that the y values are less than whatever that line is. Right, so we're going to come back to that, and I'm intentionally. I mean, I really want you to look at this in Desmos. I want you to come up with the equations, and I want you to give me the search restraint. So my purpose here is to just help you think about this. But if I don't want to just tell you an answer. I just want to help you think about it and then come up with this. And I hope that you understand what we're looking for. So there's two more basic facts of the case. Let's look at the second one. It says pilots report from a nearby airplane. It says we, on our way from Australia, when we saw a hot air balloon sinking rapidly, I am certain that it crashed south of our flight path. When we left Australia, we traveled 2,000 kilometers north for every 3,000 kilometers east we flew. So you can see this is the airport, this is Australia, and this is the airport that they left in Australia. And they're giving you two things, right? We clearly have a starting value, right? We have an XY pair, and we also know a slope. We know that we traveled 2,000 north for every 1, 2, 3 that we traveled east. 2,000 north for every 1, 2, 3 we traveled east. Now, you can use that information, right, to figure out what the equation of this boundary line is. And the other thing is it says that when we saw a hot air balloon sinking rapidly, I am certain that it crashed south of our flight path. So if this is our flight path, right, what is it? Up to over 3, up to over 3. So if this is our flight path, they said that he was certain that it crashed south of his flight path. So there's this curve, and it's below this curve, south of that flight path. So we've got two things, right? We know that one of them is this curve. We've got to figure what that is, and it's south of that curve, right? They saw him. They said they saw him near the Solomon Islands, so that's below that curve. So it's below this curve, and it's below this curve. So it's somewhere in here. Then the final constraint says, phone call received today. I was a passenger on a flight that flew directly from French Polynesia. Okay, where's that? French Polynesia, right here. I was looking out my window when I saw the balloon going down to the north of where we were flying. I was a passenger on a flight that flew. Oh, oh, it flew directly from French Polynesia to Indonesia. So the only airport that I see marked in Indonesia is here. So we're going from French Polynesia to Indonesia. So this is this flight path. And then it said, I was looking out my window when I saw a balloon going down to the north of this boundary, to the north of that boundary. So there's three constraints there. They're all linear constraints. One of the constraints you were given 2 points, and you have to figure out what the equation is that goes through those points. Another one you were given a point in the slope. Another one you were given 2 points, French Polynesia and the airport in Indonesia. So let's take a look at this in Desmos quickly. By the way, all of these will be, this map and these directions are going to be in the assignment for today, so you can refer to all of them when you look at the document. So this is the link that you're going to get um, to Desmos. You're going to see this sheet, and you can see that there's this instructions that I read in the textbook, and then there's these one, two, three uh, different reports. And it says, hint, use the reports above to write inequalities to find a possible rescue region. So where are we at? So one of the things you can do is when you've got one of these selected, you can hit plus and then do an expression like this. And it's going to graph this right below this. So if I'm looking at this, my first one went from the Philippines to, what does it say? Yes, it went from the Philippines and a flight path straight to French Polynesia. The problem that I have with this flight path is that I don't know these coordinates well. This is probably the most difficult of the three. My recollection is if you were to graph this, I think it might have a fairly decent y-intercept. And I'm trying to look at it right now. Let me zoom this in a little bit so I can put a little ruler up here. Yeah, when you graph this, you're going to get a pretty nice, I'm pretty sure I'll just give you this hint that the y-intercept is at 2. So if I looked at y equals x plus 2, that's clearly not it. Now I can make that negative x, so I've got this downslope. But you can see that's not quite the slope pattern, right? So if I'm going to go down, I could go down 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. Down 2 over 3. Let me try negative 2/3. Negative 2/3. Yeah, you see negative 2/3 is not quite right. So I'm gonna leave you here, but I want you to see how I'm exploring with this, and I'm trying to find the equation line that will go through these 2 points exactly, and I'm giving you the hint that the y-intercept is at 2. Um, the other points the other clues that I have, I think you're not going to have problems with. Um, one thing was I think that she said it was below this line. So on this, you're not going to be looking at y equals. You'll be looking at y is less than. So you can see that constraint eliminates a big chunk of places to look for. So that's what you're going to be doing. Your answer today is going to be again these constraints. So all three of the constraints typed into your Google Doc. Please use the equation, insert equation, to make it look like an equation. Um, and then also copy and paste this graph. So once you've got your graph the way you want it, include that graph. It's not greater than. Include this graph in your presentation as well. All right, class, that's it then. Homework for today are problems 81 through 87. Um, please focus on those problems. Give them a good effort, and if you are stuck, please use the resources I've made available. This is Ms. Roberts. I will see you tomorrow.